Hi students. So in the previous lectures we spent a lot of time in steady level flight or what is also known as cruise, and this is the situation where most airplanes spend most of their life. But there are certain important considerations you need to keep in mind when you are designing an airplane. They should be capable of turning flight, for example level turn, and also pull-ups and pull down. So these are actually known as maneuvers, and it's very important that an aircraft be capable of this kind of maneuvering flight because that's something which is required for its typical mission. So today is lecture 46 in our course, and I'm Dr. Ranjan Ganguly. So what we looked at in steady level flight and some of these situations is what is rectilinear motion. If you go back to your kinematics and dynamics books, which you studied in your first year or in high school, then you will know that rectilinear motion is motion in a straight line path, and lot of the physical laws or Newton's laws are essentially applied to this kind of situation. But there is also something known as motion around a curve or also circular motion. So what happens is that we are today going to look at these curve path motions or curve flight paths, and these are also known as maneuvers. So there are three cases we are going to study. We are going to look at the level turn, we are going to look at pull up and pull down. Now level turn is something which you often see an airplane make, for example around an airport. So if it's supposed to wait for some time before it lands, it essentially keeps circling around the airport. So it's in a turning flight type of situation. Now, in the case of aircraft such as fighters and so on, you often have maneuvers such as pull up, where the pilot simply pulls up like this, nose up straight in front, and he can also go through a pull down maneuver. These are very important because fighters can be involved in dog fights with fighters of different countries, and so essentially they may have to fight with fighters, they may have to fight with UAVs and so on. So they need to be able to perform very complex maneuvers, and some of these things are going to be important in turning flight. Now the key situation you will see here is that you have something known as load factor. So this number is defined as N equals L by W, where L is lift and W is weight of the aircraft. And so what happens in level flight is that L equals W, so the load factor is essentially 1. But in case you are in any of these turning flight type of situations, your load factor is typically greater than 1. So you need to generate more lift than your weight. And the unit of this load factor is G, or the acceleration due to gravity. So essentially it is measured in terms of G. So let's start looking at the turning flight level turn first. So this is the front view of an aircraft. So here I have made a typical commercial jet, and essentially you have the forces of lift and weight which act on this aircraft. So the weight of course acts downward and the lift is perpendicular to the aircraft flight direction, and so you have a certain angle here known as the bank angle. So this is given by the Greek letter phi here. So you can see this is the bank angle here, the angle between the wing and the horizontal line, and also the bank angle is the angle between the vertical line and the lift. So we are going to be able to write the resultant force now. The resultant force is going to be L square minus W square root. So you can get that from this triangle here. So this red line is the lift, this red line is the weight. So the weight can also be thought as the vector here. So essentially if we want to find this force or the blue line here, the resultant force, then that is going to be L square minus W square. That's coming from Pythagoras theorem. So that's the resultant force. Now also we can write one more equation here which will help us determine phi, and that is that L cos phi equals W. So remember this is phi here, so this angle here is also phi. So L cos of this angle is essentially this length here, and that's W. So these two equations are equations which essentially relate L, W, phi and F of R. So again remember F of R is the resultant force. It is acting toward the center of the flight path of this turning flight here. So again, this distance is typically very large. We have contracted it or compacted it today. So to show that this is essentially a distance at radius r. So this r here is known as the turn radius. It's relative to some center which is there for this circular path of the airplane which it takes in turning flight. So now let's look at the same airplane, but now we are looking at it from the top. So this is the top view of the airplane. The airplane is here. It's going around like this around the flight path here. So this is a typical turning flight as viewed from the top. So now you can see this is the turn radius r, and also this aircraft has a velocity v, and there is an angle theta with respect to the horizontal here. So now from our kinematics or theory of circular motion, we know that the angular velocity is d theta by dt, and this is known as the turn rate in the aerodynamics side of the fields. So essentially this is something we need to remember, that omega equals d theta by dt is equal to turn rate. And of course we had the turn radius. These two parameters are going to be critical in turning flight, that is turn radius and turn rate. And also we have one more equation from circular motion, that is v infinity equals omega into r. So here of course remember that the nomenclature of angular velocity, or rather I should say the unit of angular velocity, is radian per second. So you multiply by the radius, then you will get radian per second into meters, and that's going to give you meter per second. So always remember that you should take this omega value in radian per second if you are going to get the right values for the other numbers. Then the SI system will throw the right values at you. So let us just recapitulate on this very important concept of load factor, which is the lift divided by the weight unit in G. Now, if we say that an airplane has a load factor of 3, this means that it experiences a load factor of 3g, or 3 times the acceleration due to gravity. If the airplane has a load factor of 1, it corresponds to steady level flight or cruise, which is L equals W. And here the load factor is just 1g. So this is the normal situation which you have when you're flying in steady level flight in an airplane and it's going through an n equal to 1 situation or L equal to W situation. So in general, when you're performing maneuvers, the load factor will go up beyond 1, and so those numbers are going to have consequences on your aircraft and the people involved. So there are certain limits in terms of load factor. You cannot use any random large number for the load factor. What happens is there are structural limits. So if the load factor is beyond a certain limit, the structure will fail. The passengers also feel very uncomfortable at load factors which are more than 3 or 4. They start feeling perturbed. Also, there are certain maximum permittable or allowable load factors which are often used for aircraft. So for example, for transport aircraft, this may be 2.5. So that's the maximum they can take. And for fighter jets, it could be something like up to 10. Now do remember that there are some fighter jets which go beyond this also. So there are also human limitations which may be there. So just because you design a fighter jet which can structurally and aerodynamically take a load factor of 20 doesn't mean that people are going to be able to fly it at that particular G value, because what happens is that humans have certain limitations and beyond a certain G they are going to simply black out, and so you are taking a huge risk there. Now, there is a certain possibility nowadays that UAVs can handle much higher load factors, because do remember UAVs do not have any human beings in them. They are unmanned aerial vehicles and therefore they are essentially flying robots. And in such situation, if you design the structure such that the aircraft is able to take a high load factor, then you can get it to do various dramatic maneuvers and so on. So now let's look at some equations which we are going to get. We are going to get these equations for the turn radius and also for the turn rate. So let's look at this turning flight here. And now we know that there is a resultant force Fr. And from our knowledge of circular motion in high school physics, we know this Fr is equal to mv infinity square by r. So essentially m is the mass and v infinity square by r is the acceleration in the circular motion system. So we can write this as w by g v infinity square by r, where w is the weight, g is the acceleration due to gravity, which is 9.81 meter per second square if you are considering earth. So again, just recapitulate that r is the turn radius here and Fr is the resultant force which is coming because of the lift and the weight. So we can now try to write these forces in somewhat different form in terms of the load factor. So again, remember load factor N is L by W. So I take the equation for Fr, which was root L square minus W square. So this we derived in the beginning of this lecture. And then I substitute L in terms of NW here. So this equation gives me L equals NW. I put that here. So I get n squared w square in place of L square, and then I simplify it. I take the w out, so w square goes out and becomes w, and I get root n square minus 1 here. So that's the equation for Fr. So now I'm going to take these two equations for Fr, which I obtained in the previous two slides, and I'm going to equate it. So remember, one of the equations came out from Newton's law and the fact that acceleration is v square by r in the circular motion, and the second also came out from the definition of the value of n itself, and we can now equate these two equations. So that's what I have done here. So as soon as I equate it, I can cancel the w off, so the weight goes off from these equations, and I get r equals v infinity square by g root n square minus 1. So all I have done is taken r here, and here there was a v infinity square, and the n square minus 1 root term has come again in the denominator here. So this equation in the yellow box is giving us the turn radius. So now look at the turn rate. So again, we know that omega is d theta by dt is the angular velocity, which is also known as the turn rate. Now we use the fact that v infinity is omega r from circular motion to get omega is v infinity by r. Now this is again from the theory of circular motion in kinematics and dynamics, and it's coming from high school physics. So if you are unfamiliar with some of these equations, go and take a look back at your high school physics book. Then we can write r from our previous slide. R is v infinity square by g root n square minus 1, and then what I can do is I can write omega is v infinity by r. So I take v infinity and I divide it by r, and I get this equation here. So if you want to think of it, you just take this value here, v infinity by r, and so g root n square minus 1 goes to this side, and also a v infinity comes down. So this gives me the equation for omega. Now this equation in yellow box is the turn rate. So I've got these two very important equations which are measures of the maneuver performance of the aircraft. So now let's again take a look here, and I've put a fighter aircraft here because these numbers become more important for fighters. So again, if you are designing an aircraft which is a good fighter, you should have two things. You should have the smallest possible radius r, so it should turn around quickly, and also you should have the highest turn rate. So again, that will turn around quickly. So essentially, you want a turn which is the smallest turn possible in terms of radius and the fastest rate which you can get. So essentially, you can think about a situation where this guy is being chased by some different fighter or a UAV maybe, or even a missile, and he has to rapidly move the aircraft. So again, the rate at which he can move, the smaller radius he can take for the move is going to help him a lot. It can make the difference between survival or death for this particular vehicle. So let's again go back to our equations. The turn rate was given by omega is d theta by dt, and v infinity is given by omega r. So let's look at the case of low turn radius first. So in this case, if we look at this equation here for the turn radius, we clearly see that for low value of r, you should have high value of n. So highest possible value of n should be there, therefore highest L by W. And also you should have lowest possible velocity because V infinity is in the numerator. So lower velocity means lower turn radius. If you look at the turn rate, we want a high turn rate, and looking at this equation for turn rate, we see that we should have high value of n. So again, we should have a high load factor or high L by W, and also we should have a lowest possible velocity because velocity is certainly in the denominator here. So low velocity will send up the turn rate. Now, interestingly, there are some limitations to these things. Certainly, low velocity would be dictated, for example, by the stall velocity or the lowest possible velocity, which will happen when you have stall, that is when CL hits CL max. Also, the highest possible load factor is also restrained because of the structure itself and also human beings. So, do remember that 5G is the maximum acceleration most humans can take. Fighter pilots may be able to take up to 10G, but even some of that is not good for them. And beyond that, there are possibilities that things may get bad for the pilot. Generally, remember that high G is deleterious for health. It's not a good thing, so you don't want to go there. So let's summarize today's lecture. We saw that turn performance is very important, specifically level turn performance, which we looked at today. And what we need to create for good performance here is high load factor N, that is the highest L by W. And also we need to get the lowest possible velocity. So we are going to look at situations where both these are possible. Some of the important equations derived in today's class is most important is the definition of load factor itself, which is L by W or lift by weight measured in G's. Things from physics is V infinity is omega r, and omega is d theta by dt is turn rate. Also, we got the equations for r and omega. So these are the turn radius and the turn rate respectively. And these are completely expressed in terms of V infinity and n. So these two values are going to be very important. Later in this course, we are going to discuss something called the Vn diagram, which is going to actually give us the boundary within which the aircraft can actually function. So there are certain limitations here, and these limitations are going to be set by the stall speed or the lowest speed possible for the aircraft, and also by the structural damage situation. So these are going to constrain N and V, and it's going to help us design this Vn diagram. So that was the lecture for today in terms of the beginning of turning flight. So we looked at the turn, which is pretty ubiquitous in aerospace. So whenever you will see aircraft flying around, you are going to see them involved in some kind of turning flight. And they need to turn when they make a landing, when they take off, and then try to get the right direction and so on. So turning flight is something which is common to transport aircraft, regular aircraft, fighters, and so on. But there are certain flights which are more specific to fighters, for example, the pull up and pull down maneuvers. And these are things which you would see if you have ever visited any air show and seen the aircraft trying to demonstrate these patterns. So, again, nowadays aircraft are capable of going up vertically and even coming down vertically in these pull up and pull down maneuvers. So, these are two situations which we are going to discuss in our next lecture, and I will see you soon in my next video. See you then.